All right, I think we can get started. Hello, welcome to ethics seminar series. This is John, the seminar coordinator, and together with me is Miss Kathy Medley. Kathy is our communication specialist, and she and I will be today's moderator. We are excited to have our speaker, Professor Mahowald, joining us from Cornell. Just so you know that this seminar is being recorded and will be later published on our YouTube channel. Please be free to ask questions. You can do so by raising your virtual hand and we will unmute you. You can also send us a message in the chat. Let me briefly introduce our speaker before we get started. So Professor Mahowald is the Irving Porter Church Professor of Engineering in the Department of Earth and Atmospheric Science at Cornell University. And she is a co-leader working group on reducing climate risk for Cornell Atkinson Center for Sustainability. Her research group is focused on understanding feedbacks in the Earth system that impact climate change. This includes global and regional scale atmospheric transport of biogeochemical important species, such as desert dust, as well as the carbon cycle. Her group looks at these issues through a combination of three-dimensional global transport and climate models, as well as analysis of satellite and in situ data. She received her PhD in meteorology from MIT and MS in natural resource policy from University of Michigan, and she is a fellow of AMS, AGU, and AAAS, and has been a lead author on 2 IPCC reports. I will give the board to Professor Mahowald. Professor, please proceed.
Thank you very much, John, for having me here today. And for those of you who have joined here, I'm going to try to share my screen. Let's see, it's here. Yeah. Okay. Can you hear me and can you see my screen okay at this point?
Yes, it works well.
Great. All right, well, thank you all again for joining me this afternoon. I'm not talking about desert dust or aerosol biogeochemistry like I normally would. Today I'm going to talk about something that I have to say, I'm not sure that I know that much more about it than you do, but we just published a paper in PNAS about the atmospheric microplastics. And so I'd love to share with you what we learned about this. And really, I think we pose more questions than we answer in this study. It was the first comprehensive modeling study of atmospheric microplastics. So what basically happened is Janice Brainey is a colleague of mine, and she and I study phosphorus, and we've co-written papers on phosphorus and dust and other constituents and the impact on ecosystems. And so Janice published an amazing data set last year on microplastics, and so these are some of her filters that she came up with. So she put her she was looking at the national parks and wilderness areas in the western United States, and this is what some of her filters look like. And some of these things look familiar, like dust or aerosols, and then there's these blue things or pink things. And so she didn't go out looking for microplastics. They were on her filters. She was trying to figure out what these guys were, and so she did a little analysis. And basically, that's what turned into this paper that she published last year. And what she found was an amazing amount of microplastics, and she had a lot of resolution in terms of the time period of the microplastics. So it's really an amazing data set that she had. So here's her result that into these they're not all national parks, some of them are wilderness areas, but these are remote regions in the mountains mostly. She's getting quite a bit of plastics deposition. So here it's in numbers. which is a little bit hard for a modeler to deal with, but luckily, she also took a look at the size of these and converted this to then a volume, and so we can get the mass out of it. But you can see that most of the particles, the plastic particles, are actually fibers, and because the fibers are bigger, it turns out that about 95% of the mass is fibers. So she had detailed size and volume information, and please, by the way, feel free to interrupt me for points of information, and then at the end, I'm really happy to take questions, but if I'm saying something and I'm unclear, I'd love to know right away. So this is from her supplement there. She has the size of the dry and wet deposition of the fibers and the plastic particles in these depositions. So she's got 313 individual data points, including the size distributions across many of these at 11 different sites. And in total, she gets that about 2% of the deposited mass to these remote regions of the United States is microplastics. Not dust, but microplastics. And recognize also that the way she did the analysis, she and her colleagues, I should say, did the analysis is they didn't get any information about microplastics smaller than 4 microns, probably. Some of it was visually inspection in order to pick out the plastics, right? She had to be able to see that they were colored. So this was all published in Science magazine. But then a little over a year ago, she approached me and she said, Natalie, what do you think about this? And frankly, I'd never thought about atmospheric microplastics before. I don't know if you have, but I hadn't. And I thought it was fascinating, especially with this very detailed information she had about the size and when it was deposited. So that made me anyway, and my co-authors start taking a look at microplastics a little bit more, and much of the initial setting up of the model was done by a colleague working in my group, Hitoshi Matsu's framework, and then Maria Pronk, a postdoc in my group, changed it for the microplastics problem here. But as we all know, the amount of plastics and the waste generation from plastics, right, it's just growing tremendously. That intuitively makes sense. More and more things are being made with plastics. And so here's a review of the whole plastic cycle. And just to keep in mind, it's growing. The emissions are growing in terms of the plastic waste. And if you think about plastics, you could think about a lifetime distribution, right? Some plastics have a short lifetime, some have a long lifetime. But then, here, what we're talking about here is kind of macroplastics. What happens when they decay from macroplastics? Do they turn into microplastics? So we don't really know. Let's see. Now I do have a question, and now I'm trying to figure out how to pull it back up again. Chat. There we go. So Surash Basu is asking a really, really good question about how do we know that this isn't contamination, local contamination. And I should say that for Janice's data, she thought it was local contamination at first. So she went and tried to figure out how come her samples were all getting contaminated. And she couldn't trace it to, the people who go and change the filters, they don't wear that kind of plastic materials. It didn't match what was going on there. So she was very careful, but some of the other numbers you might want to be a little bit skeptical about because it is so easy to contaminate. So that's an excellent question, Suresh. So even when these macroplastics break down, then what happens to them? Do they turn into microplastics and get re-emitted to the atmosphere, move around in the ecosystems? And then also they could turn into nanoplastics, which we couldn't see in this study. Anyway, it kind of makes you wonder, made us wonder what was going on here. So just a quick review of microplastics and what people know about this. Melanie Bergman and her co-authors had a recent paper in Science Advances talking about microplastics in the Arctic and in the Alps here. And, they just had single data points in some of these, and they didn't always have the chance to make sure it wasn't contamination from them for all these cases, because that takes a lot of work. But they're seeing microplastics everywhere. in terms of in the Arctic and high on the Alps. So I don't know about you, but when I think about plastics, I think about the oceans, right? And these terrible images of the plastics that are sitting on the coast or of the mats kind of floating around in the ocean. And so we kind of wondered if that wasn't a source. There was several papers taking a look at the plastics that were caught in plankton nets. So they're smaller than 4 millimeters, but they're probably a little bit bigger than, I wouldn't call them microplastics, they're probably a little bit bigger, milliplastics maybe. Certainly most of them are probably too big for to get into the atmosphere or compared to the Brainy et al. Data. But they have quite a bit of data about the distribution here, and you can see there's a lot, you know, sitting in the gyres basically in the ocean regions, right? And so these are, you know, regions where there's there's flow around those, and there's going to be an accumulation then of the mass at the top, and this is where you get these masses of plastics. But these are, they call them microplastics, but they're a bigger size range than I would refer to as a microplastic, right? They can be all the way up to 4 millimeters, but they got these in data with the plankton nets that the oceanographers do. And so this is one synthesis of the data, just kind of showing you where in the oceans there appears to be an accumulation of millimeter sized or smaller plastics. And then there's been some papers just talking about how the estimated mass of mismanaged plastic waste going into the oceans is going up. Now we don't really know how much is mismanaged. We don't know how much is getting there, but it looks like it's growing quite tremendously. You know, doubling over a 10-year time period or so. So a lot of people are becoming really concerned about plastics and mismanaged plastics, especially in the ocean. So we had just done a study, Maria Pronk and I had just done a study with Gavin Cornwell, a graduate student with Kim Prather at UCSD, looking at the re-emission of dust. So dust being deposited into the ocean and kind of collecting on the surface of the ocean and actually being brought back up. These insoluble particles are brought back up to the top of the ocean by air bubbles in the ocean, and so they can concentrate at the top of the ocean. And so when you have the generation of sea spray, right, through waves or wind generation, just our usual sea salt source, actually the dust can get resuspended into the atmosphere. And they showed this using their super cool wind wave tunnel that they have out at UCSD. So we stuck it in our model and took a look at the impacts and, you know, published with them a paper. But so as soon as you say there's microplastics in the atmosphere, we're thinking, well, what about resuspension of the ocean sources? So, so we thought about this source and kind of stuck it in our model. And then after we had started our study, but before we had published it, Dee and Steve Allen and others in France actually went out and measured in the atmosphere for microplastics. They look at microplastics in the Pyrenees, for example. They have a nice paper also. So they were looking for ocean sources of microplastics and came up with basically the same mechanisms that we were talking about from our dust study. So they also found atmospheric microplastics coming off of the ocean in higher quantities than going into the ocean, for example. So indeed, it looks like there is an ocean source of atmospheric microplastics from the observational data as well as from this theory. Now, another potential source is agricultural fields. There's a whole literature about how biosolids that are produced in, for example, U.S. waste treatments are applied to agricultural soils, right? So you're reusing this waste and it provides nutrients to the soil. But if you have any microplastics in the wastewater, then they're going to be retained in the biosolids. And so you're presumably adding them then to agricultural soils. And so it's been measured in North America and Canada here. Then there's also, if you put plastic films on top of agricultural fields, then, you know, a certain amount of the plastics will decay and get into the field. And so there's a range, a huge range of the concentration of microplastics that's been measured in, a limited number of fields. There's not that many papers there. So then if it's a field that happens to get dry and undergoes strong wind events when it's unvegetated, then you're going to get entrainment of that into the atmosphere. And just like we have agricultural dust right now in the atmosphere, it would contain some microplastics then as well. So we postulate that as a source as well. Then there's been quite a bit of work talking about tires and brake wear. So that, when the brakes are operating on the tires or just when the tires are rotating on cars, you're going to get some little pieces of plastic coming off of that in a small size range. So it could be microplastics. And those could come from shear forces or from actually volatilization and generated submicron particles there. Now, the other thing is, of course, that it could also be like the garbage and things on the side of the road that are actually pulled into the atmosphere when you have, somebody going 60 miles an hour on a highway, for example, that could generate enough mechanical energy to loft the particles higher in the atmosphere and get them into the atmosphere as a mechanism. And remember, if you go back, what caught Janice and her colleagues' eyes was the color of the microplastics. Most tires are black, so it doesn't quite match with what she was seeing in the data that these particles were really brightly colored if they're actually only from tires. Most tires are black. So we suspect from that what we're seeing is the resuspension of plastics that have been degraded and are on the side of the road rather than purely the tire emissions. But the Evangelou paper was published while we were working on this project again last year, and they look at they estimate the tire and the brake source of plastics and then take a look at the modeling. So I can't say that we're the first atmospheric modeling of this, we're the second one, but they only look at one source and they don't compare to observations as we do. And then you got to think, well, there's a lot of plastics where humans are. So, and there are some observations of microplastics in city centers. And the problem is, what are the sources? There's a lot of speculation in the literature, but not much measurement of the sources in the literature besides what I've described here. So, so we took the model and took these postulated sources and tried to match then the data sets that the Brainy et al. Published. So we take the, let me see here. First of all, we take the tire brake source from the GAIN model, which was used in the Evangelo study. So here are the tires and the brakes. From our perspective, it could be directly emitted from the tires and the brakes, or it could be through that mechanical generation. And in addition, we assume an ocean source. So we assume in our sea spray module that a concentration of microplastics from the Van Siebel et al. Study it occurs there. So we're using that spatial distribution, and then we'll get the magnitude of the source from the model. We use the model's predicted temporal distribution of the sea spray times the spatial distribution of the microplastics in the ocean. And then we can tune it by a global number to bring it up or down. Then the ag dust and the dust downwind of population, we're using the dust entrainment and deposition module from Charlie Zender in our model, and we overlay it with a cropland area and with a deposition from population to try to take a look at, is agriculture dust the source of these microplastics, or is it kind of desert regions or arid regions just downwind of places like LA or something like that, where the plastics could have gotten there and then get re-entrained into the atmosphere. And then we also use population as a proxy for population centers, okay? Because there's really, besides the tire brake source, there's no bottom-up estimate of microplastic emissions. So we're just trying to figure out what is consistent with the data and what can we postulate. And then we're going to concentrate on the Western US for this study. So we take the model, well, we take the observations from Brainy et al. And really we want to motivate ourselves with the relationships that were found from the observations. And what they found there was a correlation with the dust. And then I was wondering about this ocean source. So Janice got us the sodium data in the wet deposition, which is all that's available. And there is a correlation there between the microplastics and the sodium, but there's a correlation between the microplastics and the dust and between the sodium and the dust. So, okay, not sure what to do with that. And then in the Brainy et al., they did a back trajectory, and they saw that the concentrations were higher in places where and when you had a population source upwind. There's 11 different stations and 313 either dry or wet deposition samples, either covering a week or up to a month in the different places. And so we pull the model results for the exact same time period. So we use population as a proxy. So the population is just a spatial distribution, and we just assume it's constantly emitting. Okay, Suresh, if that makes sense. So it has no temporal variability except for the winds as the model takes that changes the relationship between the source area and the deposition site. So we use the MERA reanalysis one-by-one model. We output every day, and of course this model already has dust and sea spray, and we're just building on an extra bit. And what is different about it is we use 6 different bins that are lighter than dust. We use about 1,000 grams per, oh boy, is it centimeters cubed? The same as water, okay? Because microplastics have about the same weight as water. And so they're lighter than dust, for example. And then we put them out there at different sizes and take a look at the distribution at different sizes. But let's talk about size, okay? Because this is crazy. How do you model this? So here, how in the world this guy is a fiber? How is this guy gonna fall? No idea. I'm fine with this cute little thing. That's spherical enough for me. This is not very spherical. So of course, I mean, the only thing I can think of that is that asymmetric is going back to my ice crystal information. So I pull out Helmsfeld, and he's got some information about what a rod will do, but none of those have this kind of aspect ratio. I mean, this is a crazy aspect ratio here. What is this? 150 micron long, and it's 1 micron thick, and then it looks almost like it's got hairs coming off it. I mean, it's it's a degraded fiber. Anyway, so I mean, what tends to happen is, of course, these kind of long, thin things will orient themselves a little bit flat to the vertical and then float down. They're not going to fall like a sphere. They're going to fall much less quickly from gravitational settling. So, so we try to take that into account by having 3 different size distributions. So this is plotted up, Brainy et al. Data, the fiber length. Then this green here, if you can see it, is actually the particle sizes. And then we kind of move the mass from the fibers into smaller sizes for the gravitational settling. So big, medium, and small. We use 3 different sizes in this paper. Because we're not really sure what they fall like, and that's going to really dictate everything about their behavior. So, I mean, these fibers are 95% of the mass, and they're not spheres, so they're not going to fall like spheres. All right. And we do a bunch of different sensitivity studies to try to figure out what the uncertainties are. So we have these different sources. We run with 5 different sources, all these different size distributions. And then we use an optimal estimation to try to get the source strength. So for each of these different sources, we try to constrain one kind of global tuning number, you could think of it, or Western US tuning number for each of these, okay? And so the model is giving you the relationship between the source and the deposition, and then we're just going to move that up and down to best match the observations then. We use a method in numerical recipes that I think works well for this kind of case where you really don't know what the uncertainties are, but you want to make sure your a priori uncertainties and your posterior uncertainties are consistent, and especially to get that 95% confidence limit. So we wanted something that in the case where it's very poorly constrained, you can understand what you know and what you don't know, because I think that provides a lot of information. So we use the dust and the sea salts to try to understand, how bad or good we can simulate these things. And we're trying to simulate long-range transport into topographically complicated terrain. And so, it's great that it's long-range transport and it's remote, but it's the hardest thing for the models to get, okay? And so, so we estimate it first using the errors between the dust and the in the model and the observations and also the sea salt, but we then modify those errors to make sure that we get the chi-square to match the number of independent data points so that you have your free parameters are actually matched. So we follow the technique there, and we actually have to increase our error estimate in order to make sure that that matches. And then we include some sensitivity studies, but so we try to make sure we're getting a reliable 95th percentile. That's the basic thing, and do a bunch of sensitivity studies so we understand what the errors are. So here's our result in terms of the percent contribution at the measurement sites here. So the most important source at the measurement sites was this road braking source, and you can see it's about 90% of the contribution at the measurement sites. And it doesn't matter too much what size we use there. It can be between maybe 70% up to 100% if we use our 95th percentiles. The ocean source, it makes a small contribution, but non-zero here. And the ocean source is, of course, really far away from the remote region. There's an agricultural dust also in the western U.S., say, from California or some of the other arid regions there, you'll get a little bit of dust coming off the agricultural fields during some seasons. And the model wants to give them some rate as well. Not too much just downwind of cities. This dust generated in arid regions right next to population centers, and the population center itself isn't optimally located to give the right source distribution there in this model. So it's close to zero, but it could be up to 10% within our 95% confidence limits. So let's see. So what that gives us then is this kind of cycle over the western U.S. So this is a slightly different budget than what's happening the deposition at the actual observing stations. But what we're getting is, most of the sources, 84% of the deposition over the western U.S. Or emissions into the western U.S. airshed is from the road and braking emissions. Get 5% from agricultural soils, a little bit from population centers, dust from close to population centers, 11% from sea spray. Okay, so once you get closer to the coast, that little bit that we think might be contributing at our remote locations gets bigger, of course. And you've got about 1,000 tons in the atmosphere at any one time in the western U.S. So we did a bunch of sensitivity studies also, not in addition to the sizes that we talked about. One is instead of using the weekly or monthly data, just have one temporal average, so an annual average at each of the sites. So you only have 11 pieces of data here in this cyan color, and you can see that the uncertainties go way up, right? That you could have between 0 and 100% contribution, right? And that's huge that we have all that resolution of the time period so that you get a little better information about the source receptor relationships. Or if you remove one site, and we only have 11 sites, so you remove one site, that's 10% of the data. And again, you're expanding your 95th percent contribution there. So these are some of the sensitivity studies we looked at here, but it tells you that having that temporal information is really important. So if we take a look at what it looks like over the region, here's California coast here, Nevada, Wyoming, Colorado, and here's our sites, right? These are remote sites, national parks or wilderness areas. The model is the background, and then the circles tell you where the sites are. And this is in the annual average here. And here's the comparison of the model to the observations for each one of our 313. And these are the different sites here with their codes from the precipitation data set network that we used. So here's the model and here's the observations. And if you look at that, you know, don't be impressed. This model did not do a great job here. We might be on the same planet as the data, you know, we kind of, there's a one-to-one line. I mean, we forced it, right, with the optimal estimation. I'm not saying that this is a good simulation of atmospheric microplastics, but this is, you know, the best we could do with what we had here. This is what it looks like, you know, the scatter plot for each of the individual data. Then you could also look at it, the annual mean here, observations versus model. And the model in the annual mean tends to underestimate. And that's, you know, the way that we did the error on, you know, these high values, especially, right, they're going to drive the means. But we add a little extra relative error because those are more uncertain, those specific events, and especially can the model, you know, match those specific events, you're going to have more relative error there. So that tends to make it so that you get a little closer to the median value than the mean value, right? When you do the optimal estimation. If you've done optimal estimation, you know what I'm talking about here, that you're not going to match, especially your high points, because you don't trust them necessarily. And that's going to lead you to an annual average that's a little bit on the lower side in the model, actually. So we could justify a higher emission than we have. And here's the contribution, say, from the road source or from the ocean source, right? And this should be obvious, but the ocean source is higher near the ocean. And all our sites are way over here. So our sites are terribly placed to get the ocean source, okay? And so it leads to a huge uncertainty, and yet we're inferring a huge source over the oceans because of this small contribution here. And there's the agricultural dust contribution and population dust. So, you know, it's really the road emissions that dominate. So these are remote sites, right? It's hard to get the dust right, the sea salts right, or the plastics right at these sites. But they do represent long-range transport. So, you know, this is one of those things where we are looking at what's carried far away, but it is the hardest thing for the models to get right. Oh, the other point to make is that it turns out when we compare the dry and the wet deposition, the dry, the model tends to overestimate, and the wet, the model tends to underestimate. So again, there's probably more we need to do thinking about the size and the interactions between the deposition and the size. So for example, I mean, I was just talking about a fiber might go horizontal and that would make it float down less fast, but actually that could make it easier for rain to hit. So the below cloud removal could be higher. So we need a lot more information about how these extremely asymmetric particles could be removed, which I'm hoping that some colleagues here at Cornell can help me with. Okay, so here we have something that might be on the same planet. I'm not positive, but this is what the model and the optimal estimation thinks is going. Oh, Soroush has another one. We're assuming it's all long distance, right? Where the sites were far from any roads, okay? But if it's within one model grid, it'll go there, right? If there's a road within the model grid that has the deposition site, it's local, it'll go there because it's all averaged at a 1-by-1 grid. All right, do these numbers make sense? So a lot of the time for this, we have to kind of go global because there's so little data here. I mean, no, I guess I didn't emphasize this enough, but the Brainy et al. Data set is 313 data points, and pretty much elsewise, there's maybe 20 other data points in the whole world, okay? So it's a huge data set for atmospheric microplastics. And that's one of the reasons probably nobody has tried to do this before, is there just wasn't sufficient data. But for our tire braking source, it's actually smaller than what they published in the Evangelo study. I'm sorry, I've got his name spelled wrong there. But it's within the range. So if we globally extend our numbers, if we extrapolate what we got for the Western US to global, okay, that's You got to take a leap of faith there, but that's the only way to compare the rest of the data. We get about 96 gigograms per year with a large range, versus they had 284 with a large range also, right? And there is a little bit of overlap in our 95th percentile. And their study, they were assuming that they knew the emissions, but they didn't know the long range transported fraction, whereas we're looking specifically at the long range transported fraction here. Now, if we take a look at our agricultural dust, the concentrations that are consistent with our model simulation of how much microplastics came up, that'd be between 7 and 400 milligrams per kilogram. In our study, that's what you would infer from our study, whereas the observations are from 0.2 to 2000. So yes, we are within the observations. I mean, it's very poorly constrained. So within that very poor constraint, our agricultural dust emissions of microplastics is actually okay. Now our ocean source, if you go global, it is 8.6 teragrams per year. So it's close to what black carbon is emitted right now. So it's huge. Could be 0 though, and it could be 22 teragrams per year. It's very poorly observed here. Like I said, there's actually been some observations where they went out in the boundary layer. They were in the marine boundary layer and close to the source there, but their concentrations are 2 orders of magnitude higher than what our model thinks it would be in that grid box that they looked at, and a little higher than where they were. So I think our source is consistent with the extremely limited data, and there's not really any more data about trying to constrain the population centers and how that's moving out the microplastics. So again, when we extend globally, what we get, right, and here we're in emissions, not in percent contribution, but in emissions in gigograms per year. Our road source, the black is if we use all the data, there's maybe a 30% range here. It's not super sensitive to what we assume about the sizes. Our ocean source, though, is very sensitive to our sizes. It's actually is the largest at the medium size, okay? And either big or small would change that. And it can be all the way up to 22 teragrams per year within the 95th percentile, but it could be 0 also. Again, agricultural dust, very uncertain, very sensitive to the sizes. Dust population is just uncertain, not super sensitive to size, okay? And then we have the other sensitivity studies, the annual and remove one site, right, which expand the uncertainty. So there's more to think about in terms of that road source, that our road source is smaller than the Evangelou study, but it could also be that their study was focused and all their observations were focused in Europe and Asia that actually put plastics into roads also. So not only do you have the plastics coming off the tires, but it could be in the road surface, and the US doesn't tend to do that. So it could be that we're getting a lower estimate also because all our data is from the Western US. We don't know what fraction is capable of going airborne to remote regions. And we don't know if it's, what's directly emitted from the roads and the tires, as they assume, or if it's resuspension, as we're kind of assuming in our study. We don't know this. This is very poorly constrained. And of course, it could always be modeling errors. Right, the ocean source could be huge, but it could be larger too, according to the observations. Let's see, I'm going to show you this, that the ag dust is actually more important outside of the US than in the US. And so again, we're, just like the ocean, we're taking very limited observations where there's not much of an impact, and then extrapolating it to places where it would have a huge impact. So that's got to make you be very concerned about the uncertainties. So for example, this is what our total modeled microplastic deposition looks like, and the oceans dominate, right? They're a huge source and a huge sink. The microplastics just come in and out of the ocean, and then some of them get on land, of course. And so this basically looks like our, we forced it with something similar to the Van Sibbel distribution of where the ocean microplastics are. But you can see, some continental sources here, and those come from, let's see here, Those come from, the road sources are concentrated. Here's the US and Europe, where people are basically and where there are roads. The ocean source is concentrated over the oceans. The agricultural dust, right? It's really kind of weak over the US where we might have observed it, and stronger elsewhere. So that's going to have a lot of uncertainties. Same thing with the population dust, right? It's very weak and much stronger here. So when we extrapolate, we're we're extrapolating pretty heavily. Now there is a little bit of other data. Like I said, this Brainy et al. Data set is by far the best data set available right now. Hopefully more data sets will come available, but there is a little bit of other data. And so when we compare to the other data, what we get is the model is a little bit under predicting in these regions again. And so yeah, it's unclear. It's also, as we already talked about, and Suresh really picked up, you can have contamination of plastics. And so this data set, Janice and her colleagues were super careful to check for contamination. And it's not clear that all these other data sets were able to make sure that they were as clean as she was able to do. We did some studies about the ocean concentrations, but so it wasn't very sensitive to whether we directly, we kind of made a simplified case of ocean concentration. We could directly use the Van Sibbel data and, get, you can see it's a little fuzzier because it's more based on data here. It didn't really change what our results were. And just to be clear, this is the observed plastics that are less than 5 millimeters. So this is the plastics collected in the trawling in those plankton nets. And the amount here, what I would call in the millimeter range, although they call it microplastics, is way, way more. The scale is completely different than this scale, okay? So again, that would suggest to me anyway that there could be more ocean microplastics there than we're deducing, that we might be on the low side, okay? I don't know what would happen, but you could think about, well, nobody knows, but what's happening in the millimeter range, you could have more mass in the micron range or the nano range or less. I don't know what the relationship is between the two of those. So we do some budgets from oceans to land and land to oceans. And for the atmosphere, anyway, we actually exclude all the coastal grid points because they mess everything up, because the model doesn't, it's a 1-by-1 grid. So it's just, you can't tell which part is ocean and which part is land. So you get rid of the coastal sites, and the ocean is a net source to the land. I mean, the land does deposit, the land sources do deposit microplastics into the ocean, but there's more microplastics going from the ocean to the land, okay? And in different continents, you're getting, different distributions. In North America, it's mostly the road source, but, in Africa, you're starting to get population dust source as well as the ag dust. This part is really big. So, it doesn't really show up so much in North America, but it gets much bigger there, and it's very poorly observed by our data set here. So, should we care? I don't know. To me, I don't know anything about microplastics. It was kind of freaky that there were so many in the atmosphere, and I thought it was a really interesting project to try to figure out what was going on with the microplastics. But they're poorly known. It could reduce crop productivity, maybe, I don't know, 5%, I don't know. Could impact natural ecosystems. It could have human health potential impacts. Anyway, people are asking the question, do the microplastics matter? And I think it's an important question. There's lots of studies about, how nasty the plastics are, and we should try to cut them. And so there's, a lot of recent studies talking about, business as usual. You're just seeing a huge increase in the amount of plastics and the amount of mismanaged plastics in the future, and there's ways to cut it. So there's several studies, looking at how much plastic emissions there are and different ways to reduce the plastic emissions. And I would say that our study just points out that the atmosphere recycles these plastics too. So maybe it's just another reason to get rid of plastics. I'm not sure that it would drive the whole problem by itself. So overall, the summary is that Janice Brainey and her colleagues in the science paper published an amazing data set, way more data and resolution than we had elsewise. And what we're trying to do here is use that to constrain something about the atmospheric microplastics sources and sinks. We tried to deduce the global size of the sources, and it's dominated by the roads, but the oceans could be huge. It's poorly observed, and then agricultural dust and population dust could also be important. And pretty much what we're arguing is the resuspension of microplastics could be really important. And maybe that shouldn't surprise you because I work on dust and sea salts, which are resuspension of particles, really. But for this size range, it's kind of hard to think about primary emissions from laundries or something emitting a huge amount, but it could be possible. We need a lot more observations, and the temporal resolution was really helpful in this study. In some sense, we really have more questions than answers from this study. And I would say in the future, of course, we need to understand how important this is for ecosystems and humans. It's really not clear from the literature whether it is important or it isn't important. I'd like to point out we did not include anything less than 4 microns because we don't have the data, it wasn't available, and it could be a lot more nanoplastics. So it could be like other, persistent organic compounds that are moving around in the environment. One could also use some of the information about the polymer type that is gotten from certain analyses like FTIR to figure out what the fundamental source was way back when. Whoops, I'm going the wrong way here. So for example, polyethylene, oxidized polyethylene chlorinated, you can get this kind of information and it'll tell you something about who the original source was then. And then, from our perspective, it's 2-3% of the mass that's being deposited in remote regions. Is this important, for ice nuclei or for snow or ice albedo impact? Especially if it doubles every 10 years in terms of the emissions, that it could be something that we actually need to concern ourselves about in the climate system. All right, let's see here. I think that was all. Yeah, that's all I wanted to present here. So let's see. I think I've been answering the question and answers. There's some more. Oh boy, I was looking at the chat window here. Okay, microplastic I think is micron sized. Macro is anything bigger than micron sized from my perspective. Sodium, yeah, sodium is everywhere. Usually we talk about non-sea salt sodium because there's so much of it is in the sea salt. But you're right. It's not the best proxy there. Yeah, you got to watch the composition of the plastics. So we didn't have that much composition information, but there's quite a bit of information about plastics. This is David Wine's question. We have not yet identified the polymers. You have to do a different analysis. That's something to do. Are there known impacts? I think the higher trophic levels. So this is Santiago's question. The higher trophic levels could be really important. But yeah, we don't quite know. Anyway, maybe you guys want to go ahead and raise your hand and speak here instead. I feel like I'm talking to myself here.
Yeah, if people raise their hand, there we go. I'll unmute you, Santiago.
Oh, is it me? Yep. Can you hear me?
Yep.
Hey, yeah, thank you, Natalie. I was wondering, can you give some idea of the typical concentrations you can have in the environment of microplastic and in suspension in the air, and how much of if you have any idea of the vertical distribution? And I'm here gearing towards, I want to get an idea if I could see them from space, if they have enough optical signature that you could see them in suspension. Oh, you're muted. Oh.
You're muted.
There we go.
Professor. Yeah.
Okay, so Santiago, great question. I looked at the AOD, of course, you know I would, and it's not that big, right? These guys are pretty big, so they don't, they're not as small. I mean, the nano guys, if there were any, they would have much bigger impact. So here's something in the supplemental information, just showing the concentration, the fraction of the anthropogenic concentration, okay, out in the middle of the ocean is actually important there in percents, maybe it gets up to 5%, okay? In the middle of the ocean, anthropogenic aerosols. So they don't get out there, okay? So yeah, so it's a really small amount. It's most important in the deposition because it's mass and they're big, okay?
Okay.
Yeah. Let's see, and then someone asked, do we have data in other parts? Yeah, we need to get funding to get more data. That is the next thing we need to do. That was a huge amount of work that Janice and her group did without funding. So at this point, you need to get more funding to try to look at other sources. Rich, do you want to go ahead and ask out loud?
Steve Smith also has. Oh,
great. Yes.
Okay,
yeah, Steve Smith is fine too. Whichever.
I'll unmute Steve Smith.
Hi, Natalie. Good to hear you. Great talk.
No, thanks, Steve. Great to hear your voice.
But what did you have to assume about if they're hygroscopic or not? And do we know what do we know about that? And could that change over time?
Oh my gosh, yeah. I mean, it's and then what other compounds they're carrying with them, right? Because anyway, so we assume that they're not hydrophobic, but they're not soluble. Okay. So basically, we assume they're like dust. And so then I think in this size fraction, especially, that's probably okay. Even if they're hydrophobic, if they're hit by a water droplet, they're going to get knocked out. But nobody knows, and they're chemically very diverse as well. So we're making kind of simple assumptions at this point, but probably some of them are philic and some are phobic, and we need to be thinking about it a little differently.
Okay.
Thanks, Steve.
So there's questions from Mike and Richard in the chat. I can read it out loud, or if they indicate to me that they want their hands, like they want to be unmuted, I can do that as well.
Yeah, so Rich, I'll answer your question here. And it's how do you distinguish population microplastics and road populations? Right. So that's what I think that's exactly what's happening here, is that the map of roads happens to work better than the map of population centers. And it's actually because the deposition that Janice and her colleagues get is kind of homogeneous. If you look, I mean, let me see if I can show you here that in the annual average, and population is way more spotty. Okay, so like in the annual means here, it's almost the same. Even Joshua Tree, here of course I think this is 9 Watt Ridge here. These areas that there's a lot of difference in the population centers there, but there's a lot of roads there, so that's more homogeneous, and so that tends to force it, the model or the optimization tends to force it onto a source that's more constant everywhere. Mike Evans, for observations, is anyone trying citizen science backyard collectors? Yes, Janice is totally on that, and I think that would be really cool to do. And so if you're more interested in that, I can get you in touch with Janice and try to take a look at that. I mean, the problem is, of course, contamination, right? Because there's plastics everywhere and microplastics everywhere. And so how do you prevent contamination? But there might be ways to do some good citizen science there. Any other questions?
I actually just got one message to me, I think on accident. Does microplastics play a role as cloud condensation nuclei?
Because of the small number of them, there are not very many of them, they're probably not important for water cloud nuclei, cloud condensation nuclei, but they could be important for ice nuclei. And so they both have kind of a almost crystalline structure, and there's so few of those guys, of the ice nuclei out there, that a very small number could actually make a contribution there. So that's probably more something that we're more interested in looking at. So that both the interaction with cirrus clouds with the ice nuclei, and then also what happens on snowpack and ice pack could be really interesting. Santiago, they're about water. The microplastics are similar to water, and so we simulated them as water instead, and it might have a little bit of impact on the dry deposition. So, all right. Any other questions or comments? I'm hoping you guys will help me understand this, because I'm only a little bit ahead of you. I've been thinking about this only for a year, and it's fascinating, but I don't quite understand all the implications yet.
I think you answered all the ones that are currently asked, but if anyone wants to raise their hand really quick, we can do the last minute. Okay, guess not. Thank you everybody for coming, and thank you, Professor, for this great talk. This was also a great question segment. And everyone, just tune in next week as our seminar series continues. Thank you.
Great, thank you very much.
Thank you, Professor. We will send you the video recording once we get it. Thank you so much.
Thank you.
Okay, have a good day, everybody.